Good morning. Good to see you again. I hope that you all managed to submit the lab reports on time. And most importantly, I hope that you all learned a little bit about the standard atmosphere and more generally about the real atmosphere as well. How many of you, I'm just curious, took advantage of the extra point opportunity for the real atmosphere? Okay. All right. That's all right. That's bonus. Just curious as to the reason why. I mean, 60 points is not something to sneeze at the onset of a course. Out of, so 160 versus 100 gives you a head start. Is it Mathematica? Time.
I think it took
like 8
hours,
hours,
a lot.
8 or 9 hours.
I was still trying, I did it all wrong, so I'm trying to redo it now.
Okay.
So,
That's okay. It's a learning experience, and I'm gonna tell you something a little bit later. But here's what I'm gonna say at this point. My purpose is for you all to learn, and actually to even enjoy doing it. So, for the extra part, I'm gonna give you extra time. So you still have another week to get the additional 60 points by doing the extra part. And, okay, so
Thank you.
that's good.
Thank you.
Thank
Now,
you.
Sure. My goal is for you all to learn and to enjoy doing it and to actually sense that you're actually making progress. Now, I hope that you all feel that you understand much better that environment, that layer around the Earth that is called the atmosphere, right? Variation of properties, what exactly is happening, the composition, and so on. Today, we're going to make some more progress moving forward and preparing the experiment to be performed next week. And let's start, and I'm going to take these off for now. Let's start with the following. There are a number of terms that are used incorrectly, interchangeably. And we're going back to the discussion that we had about precision and accuracy. And I presented precision and accuracy to a large extent in the context of quantitative results. Precision and accuracy applies equally well to the way we express ourselves and to the proper meaning of the words that we use. So here are 3 terms that we need to clarify. The first one is height. The second one is elevation. And the third one is altitude. And when one is careless about the way they speak, the way they express themselves, you're going to notice that some of these terms end up being mixed and used interchangeably. They're not the same thing. They each represent something different. So let's start defining clearly what we mean by each of these, because it's important. Height. If you have the ground and you have a building, and I'm going to put here a little pointer at the top of the building, some antenna or something like that. The height of the building is defined, or the height in general, is defined as the distance measured from the surface of the ground to the highest point of the building. That is height, h. So the height is a distance measured vertically. That's the important thing, measured vertically. This from the ground, which serves as a reference surface, to the tip of the building, the highest point. Now, you can have equally well an antenna, and the height of the antenna is this. So that's what height means. The vertical distance from the ground on which an object sits to the top point, to the highest point. Elevation. Elevation is somewhat different of the story. Now, you see here, the ground is the reference for the measurement. Is this the only reference? No, it's not the only reference. You can use a million other references. We can have, for example, a smaller building and measure the height of this building compared to the roof of the smaller building. We use the roof of the other building as a reference. We're free to do whatever we wish, but this is a particularly useful reference because it's a commonly defined and understood surface. There are other surfaces that could be used as a reference. So let's start from the following. You remember from physics a principle that tells you that if you have a tube, uneven, not necessarily even size, and you fill it with liquid, the level of the liquid is going to be the same in both branches. In other words, this line is going to be a horizontal, which is perpendicular to G. Right? This is called the principle of communicating vessels. In other words, if I pour water here, the water is going to travel and go in the other arm and come up just as high in this arm compared to this arm. And it used to be that this was a very practical method that was used to ensure that when you build a fence, the top of the fence is level. You'd use the hose with some glass tubes at the ends, poured water. One end of the hose is here, you see the level of the water. The other one is 100 meters away. It doesn't matter. The level of the water here and the level of the water here are going to be the same, as long as there's an uninterrupted communication between the two. And you could basically have a straight line and build a fence that has a level top. So, this is the story here. Now, when it comes to the surface of the Earth, the surface of the Earth, as a planet, is uneven. Mountains, and I'm exaggerating by size. And then there's some depression, there are a number of depressions, and so on. So that's the real surface of the Earth. Now, there's water in the oceans that covers part of the surface of the Earth. And you will see that part of the surface of the Earth is actually defined by the surface of the oceans. First of all, if the Earth were completely covered in water, what would be the shape of the surface of the planet, the surface of that liquid? Assume that the Earth is what it is, it has the same size. Assume that it spins the way it spins once every 24 hours. And assume that all the continents would be all of a sudden submerged. What would be the shape of the surface of the ocean? Would it be a sphere?
Yeah, it's going to be ellipsoid.
Why? So, it will not be a sphere. Why? Why is that? Because Coriolis requires flow of water. If everything is still, just turning, then there's just a centrifugal force, right? So in fact, if the Earth were to be all covered in water, it would not have a spherical shape. It would have a shape that is like some bulging at the equator because of the centrifugal force that we discussed last time. Right? So the surface of the water would be this shape. Now, to make things more complicated, there's also another effect that causes the surface of the water to be uneven. Tides. What causes the tides? The largest is the gravitational force of the moon. And this would be much farther away. So here, the pull of the moon is higher compared to the center of the Earth, and it's lower on the other side. As a result, the water here is attracted stronger to the moon compared to the Earth itself, to the center of the Earth. And in turn, the center of the Earth is attracted stronger by the moon compared to the water over here. That's why tides are high on opposite sides. There's a high tide here, and there's a high tide on this side. Okay, and these tides are moving around, the high tide is moving around the Earth because of the fact that the Earth is turning and the moon is turning much slower. Okay, so how do you know, happen to know? I'm just curious at this point, it's a side discussion, but how many hours between high tides?
12.
It would be 12 hours if the moon were to be in the same place. But the moon moves around the Earth once every, how many days? 28. 28 days. As a consequence, the combination of the rotation of the Earth and the rotation of the moon around the Earth makes the interval between high tides about 14 hours. So every 14 hours you get to see a high tide, and halfway in between you get to see a low tide. What we're left with this is the fact that the surface of the ocean around the globe is actually not fixed. So if we are to say that we would like to use the sea level as a reference for measuring vertical distance, the problem is that what is that sea level? Because it changes with time. And then there's something else that happens. When you have changes in atmospheric pressure because of hurricanes and so on, the level of the water rises or comes down. In the case of a hurricane, rises. You remember from your calculations last time that the atmospheric pressure at sea level is given in the standard atmosphere is 1.01325 times 10 to the power of 5 newtons. That is newtons per square meter. That is pascals. 1.01325 times 10 to the power of 5. This is the kind of quantity that as aerospace engineers you need to start committing to memory. How much of a column of water is required to generate this pressure? If you have a column of water, the density of the water is raw water, which is 1,000 kilograms per cubic meter. The acceleration of gravity for the purpose of this calculation, let's say, is 9.81 meters per second squared. And the pressure produced by the column of water, delta P, is equal to rho g h. So, what height a column of water is required to produce this pressure? H is equal to P divided by rho times g. Please carry out this calculation. Get your calculators out and tell me how high a column of water is required to cause the pressure equal to the atmospheric pressure.
It's newtons per pascal meter squared, right?
Pascals is the same as newtons per meter square. It's the same thing. Pascals or newtons per meter square, either one, it's the same thing.
So
10.3, just about 10.3 meters. The column of water, 10.3 meters high, causes a change in pressure equal to the atmospheric pressure. So if the atmospheric pressure, for example, in the case of a hurricane, drops by, say, 5%, what's 5% of 10.3 meters?
Or
0.5 meters, just about half a meter. That's how high the water rises in the case of, just because of the fact that the hurricane in its center has lower pressure. The pressure, in the atmospheric pressure in the eye of a hurricane is lower. For example, if it were to be lower only by 5% compared to the baseline pressure of the atmosphere, that would cause the level of the water underneath the eye of the hurricane to rise by half a meter. That's a good significant reason. That's another reason why the sea level around the world is not constantly the same, it varies with time. Yes?
So would this height be from the bottom of the ocean?
No, this is how much it rises from the original,
Okay.
just because of the eye of the hurricane. From whatever it was before, it rises half a meter just because the decrease in atmospheric pressure. So, when you want to use, if you would want to use the sea level as a reference for measuring vertical distances, the problem that you encounter is the fact that the sea level is not constant. So what do? Here's what you do. You use the mean value. We call that mean sea level. MSL. The average sea level around the world. And now we come back to this figure and assume that this surface here, that I'm representing as such, would be the mean sea level. And you see that in the case of the regions where you have ocean, this is the sea level itself. The mean sea level would be a sea level. Underneath geographic features that rise above sea level, we can imagine this extension of the sea level underneath all land. This is the surface that is the mean sea level worldwide. So, elevation is vertical distance measured with respect to mean sea level.
Will we do any AGL conversions in this class?
Any,
AGL conversions?
hang on,
Okay.
we're getting there. So, it is the vertical distance measured with respect to the mean sea level. So let me come back here, and probably this is a better place for, as far as the camera is concerned, for me to work. Unfortunately, the desk gets in the way. Let me do the following. Let me assume that this is the bottom of the ocean, this is a mountain, and this is some place where you have features. For example, this would be a runway. Let me assume that this is the line, the reference line, which is mean sea level. And I'm extending this line underneath. And I don't see here the curvature of the Earth, but you understand that at the large scale, the curvature of the Earth also causes a curvature in the mean sea level. So, elevation, the elevation of a point, for example, the tip of a mountain, is this distance, E, the elevation of the mountain. This distance here to the runway is the elevation of the runway. So that's what elevation means. The distance measured vertically to the reference surface, which is the mean sea level. And even if you are on land, and particularly when you're on land, that means this distance all the way. Imagine that you drill a hole and up to the point where you would reach this mean sea level. Obviously, there is not water underneath us. So this is an imaginary surface. But that's the basic idea. That is what elevation is. And now the last concept, I'm going to erase over here. Is the concept of altitude. Altitude represents distance measured vertically from an airborne object. Two. And now we have different choices of reference system. So let's say that we have an airplane flying over land. And then here's the mean sea level. This distance is altitude MSL. Altitude with respect to the mean sea level. But as the airplane continues, when the airplane is here, this represents altitude with respect to the ground, AGL, above ground level. So altitude, two kinds of altitude, two forms of altitude, is altitude, the vertical distance measured to the surface of the earth underneath the airplane, that's altitude AGL. And this is the altitude MSL. Now, you can also have an altitude MSL when the airplane is over ground, because you extend this line here. So this distance, let me do it differently. So this here is altitude AGL, and this distance is altitude MSL. The airplane is in exactly the same position. If I only measure the distance to the ground underneath, that's AGL. If I measure the distance all the way to that reference surface, which corresponds to the mean sea level, it's altitude MSL. And the difference between the two is what? The elevation of the location underneath. So you see that altitude MSL is equal to altitude AGL plus elevation of land underneath. Does it make sense? Okay, so now we know as aerospace engineers that height means one thing, elevations mean something else, and altitude means yet something else. And altitude comes in different kinds. So, if we talk about the airport in Arlington, and we want to refer to its height above the mean sea level, what is that? Is that the height, or is that an altitude, or is
Elevation.
it elevation? Exactly. The elevation of the airport. So if you talk about the height, well, if you talk about the peak of Mount Everest, is that the height, altitude, or elevation?
Elevation.
Elevation, that's right. Mountains have elevation. If you talk about the building next door, the vertical distance to its top, that's the height. And for airplanes, we talk about altitude. Now, when flying airplanes, it is very important to know how high you are, to know your altitude. Among other things, because you want, first of all, to avoid controlled flight into terrain, hitting the ground. You also want to make sure that you avoid other airplanes. So knowledge of the altitude for a flying object is extremely important. So knowledge of altitude defines what is called as altimetry. The measurement of altitude, altimetry. Altimetry is an essential ability and essential technique for flying. Without being able to determine and to measure and to know your altitude, flying would be very difficult and very risky. So altimetry is a fundamental requirement for being successful at flying. Historically, the first form of altimetry is based on measurements of pressure. And let's ask the following. You learned about the standard atmosphere. Now we're coming full circle to our discussion. You learned about the standard atmosphere. You learned the fact that there are three parameters: pressure, temperature, and density, that define the gas, define the properties of the atmosphere at any altitude. And you learned that each of these is defined by a number of equations. And you saw the equations, you read the equations in the textbook, you used them in the notebooks, everything is good. If you look at the function of altitude at the variation of pressure, you see that in the standard atmosphere, the pressure starts from the pressure at sea level, which is that value, 1.01325 times 10 to the power 5 pascals. And as the altitude increases, the pressure goes down like so. If you look at density, the density as a function of altitude also starts from a particular value, density at sea level. How much is that? 1.225 kilograms per cubic meter. 1.225 kilograms per cubic meter. That's the density, the standard density in the standard atmosphere at sea level. This is another value that you as aerospace engineers need to commit to memory. And the variation with altitude looks kind of like that. You saw that in the book, in the notebook, and so on. Finally, if you look at variation with height of temperature, you saw that the temperature starts from temperature at sea level, which is how much? 288.15 Kelvin, which is the same thing as 15 degrees centigrade. These are values that also you need to remember. So the standard temperature at sea level in the standard atmosphere is 15 degrees centigrade or 288.15 Kelvin. And the temperature varies kind of like this. So up to 11 kilometers, it decreases linearly. From 11 to 25 kilometers, it stays the same. Then it increases, and so on. That's how the properties of the atmosphere vary with altitude. Now, we want to measure altitude as we fly. So we would like to ask the following question, having learned about the properties of the standard atmosphere. Do you think we could rely upon measurements of the properties of the atmosphere where we fly to determine the altitude? Yes or no?
Well, it depends on what instrument you're using.
Okay, it depends on instrument. Let's first of all, let's see if there's a dependence on what it is that you measure. Let's assume that we want to use pressure as the basis for the measurement. We measure a given pressure, and with that knowledge of that measured pressure, we go, and there's your corresponding altitude. And because this curve is monotonic, we can do that. For every single measured pressure, there's one and only one altitude that results. So yes, pressure, the measurement of pressure, could provide the basis for measuring height indirectly via pressure. And the height that you measure this way is called pressure altitude. So, the definition is the following. Pressure altitude represents the altitude in the standard atmosphere at which the pressure that has been measured is encountered. You measure this value, and this value corresponds in the standard atmosphere to this height. That height is pressure altitude. Yes?
Can pressure fluctuate because of like storms and stuff like we were talking earlier?
Okay, we're gonna go to that. For the time being, we're considering that we're dealing with a standard atmosphere. Everything is fixed, everything, so with the question we're asking, can we perform measurements of altitude assuming a standard atmosphere? So if we want to measure pressure, yes, the answer is yes, we can do it, and what comes out is called pressure altitude. Pressure altitude is an altitude. It's not a pressure. Pressure altitude is an altitude. Now, can you measure easily enough pressure? Yes, you can measure pressure. There are a number of ways. There are instruments to measure pressure. So, as far as pressure is concerned for altimetry, it is both practically possible to measure pressure, and it is also possible, based on the way pressure varies, to determine altitude from pressure. Are we on the same page? Good. Yes.
How about speed of sound?
The speed of sound. We'll come back to that. Hold your question until I'm done with the third. Now, any other questions? Good. Now let's go to density. So let's assume that we measure somehow the density. And then based on that density, we determine a height in the standard atmosphere where that density takes place. This would be called density altitude. It's also an altitude. It's the altitude in the standard atmosphere where the density that we measure would be encountered. So yes, because of the variation being monotonic, then you can measure a density and get an altitude from it. But is the measurement of density an easy measurement? No. So in principle, this measurement could allow us to measure altitude, but it's not practically possible. Now let's go to this one. How do you measure temperature? Easily, with a thermometer. Let's assume that we measure the temperature. That's the distribution of temperature in the standard atmosphere. What is the height that corresponds? What's the altitude that corresponds to this temperature? Well, it can be this one, or it can be this one, or it can be this one. Oops. There's a problem. You cannot use the temperature to measure altitude. You cannot hope. There's no hope to be able to use a thermometer that you stick out the window in an airplane to tell you how high you are, what the altitude is. So this is not possible. And it is the way the non-monotonic variation of temperature with altitude that prevents it. So altitude, pressure altitude, density altitude. There's no such thing as temperature altitude. Are we on the same page? Everything is good. Yes.
So pressure altitude is an altimetry?
Pressure altitude represents an altitude at which the measured pressure appears or occurs in the standard atmosphere.
Right.
All right. Now, any other questions? Or did the answers, they clarify your
What was the
question?
word that you said,
Monotonic. Monotonic. The function is monotonic if it varies uniformly in one direction, either decreases or increases. In the case of temperature, at first it decreases, then it increases, it goes back and forth, it's not monotonic. All right, so this form of measuring altitude, based on pressure, is the most important one because it both offers a way to do it and it is practically possible to measure pressure. This is called barometric altimetry. So barometric altimetry is a technique of measuring altitude by measuring pressure. You determine altitude by measuring pressure. All right. Now, let me erase this. And put up the following. What's the fundamental equation that allows this? Remember we had the hypsometric law? Delta P is equal to minus rho G delta H. Or in differential form, dP is equal to minus rho G dH. The finite difference in the infinitesimal form of the hypsometric law. The change in pressure corresponding to a change in vertical distance, vertical location. All right. Now, this is the first form, barometric altimetry. Barometric altimetry is the first form of altitude measurement since the beginning of flight. And to this day, every single airplane flying around is required to have a basic instrument that performs measurements of altitude based on measurements of pressure, a barometric altimeter. So the instrument used to perform the measurements is called an altimeter. The altimeter is the instrument, and again, there are a number of physical principles that can be used, but the one that's the most fundamental and the one that we're discussing today is the barometric altimeter. So the barometric altimeter is an instrument that is present in every cockpit of every airplane or flying vehicle, and it has a face of an instrument that I would like you to be familiar with. So for that purpose, this is on, HDMI is on. Let me bring that up, and we'll discuss in a second. All right, light. And I'm going to show you a typical face of an altimeter. This is the typical face of an instrument. The indication here is that every single scale unit corresponds to 100 feet. The instrument